So there's no need to present Roberto, you know him already. And I will introduce shortly Michael Farrow. So Mike is also an engineer, who would have thought, working in the safety, technical and engineering department of Network Rail, which he joined in 2006. In Merlin, Mike has been the technical lead for Network Rail's involvement since 2012, including the management of the two scenarios that he will be presenting now. So, as I said, we will not introduce Roberto again, and we will start the short video clip. Thank you.
The West Coast Main Line is one of the busiest mixed-use traffic lines in Europe. We've got 43% of the UK's rail freight uses the line, and we wish Scenario 4 to focus on a line in the north of England, on the north end of the route. One of the biggest problems that we face is that whilst lines are being upgraded, there are electrical constraints which limit the number of electrical trains that can operate on a given route or section of line. So what we'd like this scenario to do is look at how, given a particular service pattern, we can best utilise the mixture of diesel and electric services on the line to give us the best energy consumption.
Scenario 4 deals with the West Coast Main Line, and the objective is to find a strategic decision onto what is the trade-off between using electrical traction or diesel traction. This will be with the objective to minimize both electrical consumption and diesel consumption within the network, and therefore optimizing the energy consumption. For this purpose, we used a newly developed tool specifically for this project called the Strategic Decision Making Tool, SDMT, which takes advantages of the existing railway simulation tools like the one provided by Network Rail called Vision Oslo. We looked into the timetable and trying to identify of all services which of these could be actually potentially using either diesel or electrical traction. We focus on the freight services, which are the only ones that could do this, and we identify 19 of those. Once we plot all the results into the graph, we obtain this Pareto front optimum graph, and that will give you all the necessary information to make an informed decision about the trade-off between electrical traction or diesel traction in these particular services. As an example, we picked some random points on the graph and we looked into the meaning behind all the data there. And we found, for instance, there was a particular combination of 10 diesel services and 9 electrical services that will give us a lower energy consumption. These results give you proof that we can actually use these sort of strategic tools to make decisions that will allow optimizing energy consumption in a long-term perspective.
Okay, thank you all. I'm just going to go through some technical details of the line now in the few slides before I'll let Roberto take over and talk more about the results that were obtained. So, the aim of Scenario 4, as we mentioned, was to investigate the use of a busy mixed-use railway line, and part of that, and the major part of that, was strategically identifying the type of propulsion and mixture of type of propulsion for energy against energy and electric traction for a growing demand of railway where the upgrade of electrical network doesn't necessarily always meet the demands of the services. So here is a map of the scenario that we've just explained. So the line is the red line here, going from just south of Preston to here near Penrith, and this diagram here shows the diversity of train services and the different lines that come off there and branch into areas such as Blackpool, which is a important holiday destination in the UK, and also various industrial places up and down the northwest of England. Here we have a diagram showing some of the gradients along the route. One of the important considerations about this line is that there is a very steep climb up to Shap, and if we were going to, although we didn't in this case, but if we were going to look at the operational restrictions and operational characteristics of this line in the future, then we would look at the operations around this point and the passing loops that are in place with regards to how you move your train services and ensure that you've got a credible movement of train services against each other in terms of driver advisory systems, but also that perhaps interacts with train energy performance as well. So I'll also briefly touch upon the simulation tool that we used. The simulation tool was Vision Oslo, which is a multi-train simulator which was developed by British Rail Research in the 1980s and has obviously since been refined and developed and was used as part of the modelling for this scenario. So I'll pass over to Roberto now to talk through the results. Thank you.
Right. So, me again. Hopefully you will understand better than in that video, which I have a really bad cold, so I was very nasal. Anyway, so SDMT, I presented this before, so these are some screenshots of actually the user interface, which was one of the new modules that we developed, as I mentioned early this morning. And so these are the two tools that we employ in this particular case. So in terms of the simulations, basically, looking at the topic, at the objective, we have 6 parameters, and we needed to decide how we were going to be fixing those parameters. Again, if you cast your mind back just a couple of hours when I was talking about the different design vectors, well, these tell us what is important, what is not important, what we want to optimize and know. So obviously, there's a target to minimize the total energy and electrical energy consumption. That's clear. We have a constraint in this particular model for the power that we can draw from a substation because of constraints of a very busy line with maximum power already being drawn. The total energy cost is irrelevant because of the contractual arrangements in the UK didn't really allow us to do anything else. So we were not looking at costs in this particular case. It's fixed, you cannot do anything about it in this particular scenario. Then obviously capacity and journey time were constant because the timetable was not going to be modified. We were going to work on the existing timetable. And finally, obviously linked to the first target, minimizing diesel consumption, the dirty word diesel. We're using diesel in this project. So these are the constraints and the target. So you've seen this, so we apply this, okay? So this is Vision Oslo in this particular case, the multi-train simulator from Network Rail that we work on that. This is the SDMT, and we carry out the optimization. So basically, mainly these two modules were the ones that we were using in the simulations. So because we're trying to optimize the balance between diesel and electrical traction, only diesel services are the ones that can actually do this, because passenger services are all electric, it's an electrified line, so you have diesel multiple units, you cannot change that. So the only services that have enough flexibility to choose one of the two traction modes are diesel services, just change the locomotive. So we look at the timetable and we identify 19 different services that were suitable for this, and they're listed there. Then we put all the magic box and we came up with this graph, okay? So in a way, it's a logical graph. You cannot read it, but it doesn't matter. So the bottom, the x-axis is the diesel consumption, and this is the electrical consumption. So logic tells you, you don't need a simulation, that if you increase the diesel, you will reduce the number of trains that are running on electric. So that's clear. What is not clear, and that's what one of the first results of this, is what is the angle of this trend. This could be, they have different angles, could be really sharp, or it could be flatter. So that is the first result you get. We have an understanding of that trend. Every single point of that is a combination of those services. So behind each point, there's a lot of data-rich information, okay? So to illustrate what you could do with the tool, because at the end, this is just a way of trying to demonstrate the methods and the tool that we developed, we looked at 4 particular points in there. And what we looked at is the different combinations those points gave us. And looking at them, there's the services, and each one of the services, there's a particular combination. So we look at the results and look at which ones over there, nominated and non-dominated. And you don't have to remember this, but I said this morning, it's about, the optimization was based on non-dominated, basically the Pareto front stuff that I was talking about earlier. So needless to say, just here that we found one of these combinations was the most optimum one. You could not improve any better. So this gave us an example of how you could actually do this. Okay, sorry, too close, too far. So to conclude, the first thing you can see in the first couple of bullet points, we find out that indeed you can actually find a combination of freight services that use different traction modes to improve your energy consumption in a line. So that's something that can be done. So that's a result in itself. It was the scenario result, but it was not the main objective of the project. Nevertheless, you get a result that you could do this. So there's ways of optimizing energy by choosing different traction combinations. By the way, it's 19 combinations in this case, but it doesn't mean a number. It doesn't mean 10 and 9. It's which 10 and which 9. You could have 10 and 9 and completely different 10 and completely different 9. It's which one of those, because each service has a different pattern, different stopping pattern, different paths. And the second batch of conclusions was that indeed, gone too far. The previous one, the next one there. Indeed, the tool, the methods, rather than just the tool, because the tool is just based on the structure, on the architecture. So the architecture works. The methods that we looked into for optimization, for a strategic design, for this sort of thing, actually work. And you could use them to guide. And this is important, just to guide. It doesn't give you the answer. It gives you enough information for guiding you towards what is more important for the user. Okay. So in that sense, we proved that this kind of works, and I think that's all for us. Yes, it is. So thank you very much.
By close cooperation between research and industry. The synergy between these two...
Oh, I think we hear the interpreters, no? Are we? Okay, so we keep Michael here, and we call the second speaker for Scenario 5 on the floor, who is Carlo Crovetto from AnsaldoSTS. Am I correct, Carlo? Yes? Carlo is an electrical engineer working at AnsaldoSTS, where he has been working in the innovation unit since 2014, with the role of senior innovation and security engineer in the forthcoming European project Shift to Rail. Carlo will thus present the solution developed by AnsaldoSTS in Scenario 5, optimizing energy infra and management of a regional line in the United Kingdom. But before that, we will see a short video clip of Scenario 5. Thank you.
Scenario 5 looks at a section of the line in the south of England where we have a large network of 750 volts DC electrified lines which run via a ground-mounted third rail. One of the key questions that we'd like to answer is whether we can optimise, given the space constraints that we have on our network, the location of a substation and its no-load voltage during a renewal. And what we'd also like to do is then look at whether a REMS could be useful to us in the future to optimise the energy consumption for given trains during periods of a disturbance such as a circuit breaker outage.
AnsaldoSTS within the Scenario 5 has performed a lot of simulations using the SDMT and REM tools. And we are now very close to the end in order to find the best solution for one railway's lines with the positioning of the substation and the voltage, no-load voltage of the substation itself.
Okay, thank you again. Again, I will talk briefly about the electrical network that we have and then hand over for the results. So I think somebody asked in a meeting on this project about 2 years ago why we're investigating a metro railway. And I said, well, actually, it's not a metro railway, it's a mainline railway. But we have about a third of our electric network is actually running on a third rail 750 volts DC system. So that is powered by, in the case of the line that we'll be looking at for this presentation, 11 kV network, which runs parallel to the railway. Along that line there are multiple substations, roughly around 1.5 kilometres in spacing. Some of those substations are they are just paralleling points, so there is no in-feed of electricity from the 11 kV network there. And as you can see here, we've got 8 substations, 6 track paralleling huts. The approximate journey length for the line we're looking at, which is Bournemouth to Weymouth, is about 60 minutes or so with a 30-minute frequency. And that just gives a bit of a geographical representation of the line. So strategically it's very important to us because there is increased traffic on the railway network, as I'm sure is seen on other parts of Europe as well. So in the UK, it's gone up considerably since where we were in the 1990s, and there are a number of direct services to the capital of London from Weymouth and Bournemouth, which is the start of this particular study. So what we wanted to do here for this scenario was, as I explained in the video, evaluate energy management and optimization of Scenario 5 and reduce energy consumption and power peaks in the case of a disturbance along the route. So the 2 parameters we wanted to optimize were looking at we're looking at the substation location along the route and also the no-load voltage. Now, you may not consider the low-load voltage to be a significant factor. You may think, well, it needs ultimately it needs to be as high as practicable within safety reasons. But a lot of factors can influence that on a railway where you've got a paralleled up, continuous line of energy flowing through. In a DC system, you don't have the breaks that you would find in an AC system, and so on our network in the UK, we found that actually there are some substations that are quite close, that are very similar in their low voltage, but they can consume very different amounts of electricity dependent on the train stopping services and whether they're braking or coasting or accelerating past them during the day. The other thing we wanted to look at as part of this was whether the REMS could be used to cope with breaker operations on our line. So sometimes a breaker is taken out of service for maintenance, or sometimes a breaker trip happens because of a faulty train or an overload on the line, or short, say an animal running across between the third rail and the running rail system. So I'll hand over to Carlo now to talk about a bit more about the methodology and the results that we found.
Good morning. First, you will forgive me if I am not Matteo, that was represented in the clip movie before. Just a little speech about the approach to give a solution to the problem, to the issue by network rail. Okay, we have exploited both the strategic decision-making tools approach, as well as later on we will see the railway energy management system tool. The first one, the parameters to be changed were the maximum the no-load voltage in the two substations individuated that were Winfleet and Redlands. So the minimum voltage could be 700 volts and the maximum 900 with a voltage step of 50 volts. And the other one is the location of the substations themselves. So plus minus 500 meters with a deviation steps of 250. Okay, we can go over this one. No. Okay. The baseline model was the current situation for the two substations in terms of no-load voltage and the location, of course. Let's have a picture regarding the overall process. We start defining the objective design variables, then the calculation of the parameters and the first iteration, the first running of the algorithm. And then the results will be managed by our own simulator, that is an electromechanical simulator called Trains Runner. We, in that occasion, used the simulator to calculate the energy consumption for each of the scenario that was proposed by the MERLIN simulator. So this is the picture graph interface with the user, the selection of the position of the substation as well of the no-load voltage. And these are the 5 scenarios first proposed by the core module after with the process of all the data. For each of them, we have calculate the energy consumption, that is the red line in this picture. And since the algorithm could not give at the first running the convergence, there was another iteration, another step in the loop of calculation, and 5 further scenarios was proposed and are here highlighted in green. Again, we perform the calculation for each of them of the energy consumption, and in this second step, we could get the convergence, and the solution that was the winner was the red line. The target, the consumption is very, very close. It's equal to the current situation, and this is the demonstration that the engineers that designed at the time the line made their work in a proper way. Okay. So the second application is for the railway energy management system. Okay, let's go on the definition of the DAO or MAO. The baseline scenario, we get the previous one in terms of substation location as well as no load voltage. And the case study was the out of service of the Red Lens substation. What we mean with out of service, we mean that the rectifier and or transformers group are disconnected, but all the high-speed circuit breakers are closed in order to allow the continuity of the third rail section. Okay, there are 7 steps of the process. The first one, in this case, is the calculation itself by Trains Runner tool, by our own simulator tool. We calculated for each substation the power profile, and for each train, including the slot that the network rail indicated us, the power profile again. The slot was a morning slot starting from 8:30 and lasting 20 minutes up to 8:50. There was the preparation, of course, of the MIO estimation file and configuration file, and then the running of the REMS tool, whose result is an indication for each train in the slot that could be affected by a limitation of the power absorption. We, okay, again, it's a picture regarding the graph interface. Okay, this is the train that was not affected by any kind of limitation, just for instance. Okay, let's go to the result. This was the profile in the Branksome substation that is the worst loaded in this specific case study. This is the power profile without any kind of optimization. And you can see that the power peak is very close to 2,500 kilowatts. After after several times of repetition of a loop, the power limitation could get a reduction and a smoothing, but above all a reduction up to 2,200 kilowatts. That is more or less 8–10%. So it's perceptible and appreciable. Our first goal was a little bit better, was 180 kilowatts, but the service would have suffered too many limitations and was not acceptable from our perspective. So the conclusion regarding the application of the first methodology is that we could get any reduction in consumption, but maybe, not maybe, surely, because the original choice of the parameters was negligible, against this kind of matter. Maybe the location of a substation was too close, and so was not possible to get any improvement. But the methodology itself shows that there is also a result, that is that any benefits could not be reached in this case for that reason. And regarding the second approach, the result was very appreciable because the peak shaving was up to 10%. Even if we have no evidence of other impacts on the whole traction system. So the target was achieved, the object of the study was achieved, that was minimize and smoothing the power peaks. Just last consideration, maybe at the current level of development, the tool doesn't take a very holistic approach, giving only, in this specific application of course, giving only indication trains power shaving. So this is just a consideration, a final consideration. Okay, thank you for your attention.
Thank you very much, Michael and Carlo. So, after the 5 scenarios, we will now present the recommendations for market uptake and implementation, and also standardization. On the floor, we have Eduardo Pilo, who is Master in Science and PhD degrees from Comillas Pontifical University in Madrid. Since, very rapidly, since 2010, Eduardo has been the Chief Executive Officer of EP Rail Research and Consulting, a company focused on power systems and railways. We also have Ignacio González, who is an industrial engineer who holds a Master in Science in Railway Engineering. Ignacio is a researcher of the Study and Research Group for Railway Energy and Emissions, and coordinator of the study of the Research Group for Technical and Economic Transport Operations of the Spanish Railway Foundation. Both Eduardo and Ignacio have participated in the elaboration of the global consumption maps. They have conceived and developed the energy buyer decision maker, and also have led the position paper on network integration and the guide for implementation. So gentlemen, the floor is yours, and I give you the remote control. Thank you.
Okay, thank you, Isabel, for the presentation. In this short presentation, there's an important idea we would like to throw into you, which is especially an important idea for the future, which is by implementing to implement these new technologies, these smart grid concepts. Well, it is not just a matter of buying a new box, a new equipment, and just installing it. It's not just a new box. It's really about the evolution of the concept of how the electrical railways are designed and operated. And we are talking about the migration from a just offline concept in which everything can be planned and optimized in advance, but then there's the real time and there's little we can do to a situation in which, in addition, we can perform an online optimization which allow us to adapt to the changing conditions of real operation. We're talking about being able to optimize when something changes so that we adjust the operation to the evolving, to the unexpected. In this condition, it is very important to realize that not only the IT systems, the IT technologies have to be developed and implemented, but also modifications in the operation procedures, for instance, to include a step in which the railway undertakings provide power profiles or information related to the expected operation for the following days is provided. Also, modification in the regulation, not only at a European or at a national level, but also internal procedures of the railways companies, how everything is done. Those may be necessary because once more the technology may be able to offer possibilities that are not contemplated in those regulations and which we wouldn't be taking advantage of. For that reason, in MERLIN, there was a specific work package 7, whose purpose was to elaborate a set of recommendations for market uptake, for implementation and standardization. More specifically, there were four documents, public documents, that have been produced. The first one is a position paper for agent integration and interaction. There are 2 proposals for TechRec, one focused on the railway energy management system architecture, and another focused on the exchanges of information and the communication protocols at an operational level. And finally, there's a document with guidelines for implementation of this network integration. Focusing on the position paper for agent integration, this document specifically describes the technical and economical aspects of the adaptation of the electricity distribution in the railway sector when the smart grids are implemented. As we can see in this graph, this picture represents the flows, the economic and the electrical flows in the electricity supply to railways. In red, we can see the electrical flows that go from the power plants in the left side, cross the national transmission grid, then cross another smaller voltage grid, which is the distribution grid, and finally cross the railway's power system grid until they reach the trains. The economical flows are a little bit more complex because in the current situation, normally the railway undertakings buy the electricity to the infrastructure manager, which in some cases it's split into an electrical infrastructure manager and just railways infrastructure manager. And it is those infrastructure manager which performs the last hop of the distribution activity, which buy the energy to different suppliers or to the market or directly by any kind of agreement to the producers. In a wider perspective, in scanning what the future situation could be, what we find is that, of course, the trains well, we will still have a relation with the infrastructure manager, which is this railways distribution grid, and of course we'll have to pay them for this distribution activity. But in what is related to the energy itself, the energy supply, they may be able to select other energy suppliers. For instance, one of these electricity supplier may be the infrastructure manager itself, acting as a specialized energy supplier. In this situation, it is very important to realize that the developments in MERLIN may help to reduce the main challenges when related to energy supply, which are the volatility in the prices in the market and also the volatility in the estimation of the demand. Now, with a smart grid, the demand may be more predictable, and therefore the risk, the economic impact of this risk may be mitigated. Regarding the interactions with the transmission and distribution grids, it should be noted that now, with MERLIN technologies, with the smart grid technologies, the railways are able to respond to the needs, to the online, real-time needs of the transmission and distribution grid. For instance, if there is any kind of power limitations in the distribution side, the railways could adapt. Of course, related to the economic flows, they will still exist, but an additional service may be offered by the railways when the grid, the electrical grid, offer it. Finally, there is an important part in the interactions, in the internal interactions between all the agents inside of the railways electrical grid. It should be noted that one of the most important news is the fact that there will be two kinds of trains. Trains that just consume energy as they used to do, which pay for it, which may regenerate as they do. But in addition, there will be new kinds of trains that are able to respond to the needs, to the instructions that the control center gives to improve the operation. Once again, the smart grid can help in that. In addition, it is important to highlight that new types of agents may appear. For instance, it could be possible to have a specialized railways undertaking which offers the service of regenerating or not, or just operating an energy storage system as the system needs it.
Thanks, Eduardo. So let's continue with the explanation of the document that we deliver in this work package. In this work package, as Eduardo mentioned before, also provides with two proposals of the RECs. The first proposal of the REC is called Railway Energy Management System Architecture and Location of the Energy Meters in the Grid. It's a long name. So the main objective of this proposal is to describe the architecture of the REM system, including functions, component layers, and the key elements of the different subsystems developed in MERLIN. In addition to this information, this proposal of the REC also describes where the measurements equipment should be placed in the grid in order to achieve an integrated energy management. Okay, the second proposal of the REC aims to establish, as it was mentioned by Eduardo before, establish the standardization of the information exchanged between agents in terms of contents, format, protocols, sequence of messages, and its periodicity. The content of these two proposals of the RECs has been already defined by Valeria. And that's why I'm not going to explain it in detail. But it's important to highlight here that we have developed two proposals of the REC in order to standardize two questions. Those are the two issues that we have addressed in MERLIN. The first issue is the architecture of the REM system, and also another issue is the information exchange between agents. Okay, I'm going to explain now that the last task carried out in this work package, the guidelines for implementation. The objective of this document is to provide a guidelines for the practical implementation of the different subsystems developed in MERLIN. And for each of these subsystems, a brief description is provided, centered of their functionalities, their inputs, outputs, etc., and also a progressive implementation description of each of these subsystems is also included in this document. Due to the large amount of investment required, the implementation of a smart grid like MERLIN should be done progressively. The smart trains and the smart infrastructure will have to coexist with traditional trains and traditional infrastructures. That's why we think it's convenient to include a progressive implementation, deployment in phases section in this document. However, in order to provide some criteria for the progressive implementation, the interdependencies among the subsystems specified in MERLIN should be described too. But what do we mean with dependencies analysis? This is an example of the dependencies analysis for the REMS module developed in MERLIN. The idea here is to explain the interdependencies between functions, in this case for the REM module, for DAO, MAO, and RTO functions. And the idea is to analyze if they can run independently, or rather than they require some inputs from other functions in order to work properly or for obtaining the expected results. For example, in the first row, for the DAO function, is required the MAO function and also the external multi-train tools. Not the external, the result of the external multi-train tools. That means that the DAO function doesn't make sense without the MAO function and the external tool to simulate the driver profiles. As a summary of the REM system, the REMS module, the MAO function is required by the rest of the functions. It can be said that this function is essential in order to work properly. Okay, I don't know if it's okay. Once we know the dependencies between subsystems and functions, we can carry out the develop in phases analysis. This is an example for the REM system, the same module that we have explained in the previous slide. And the REM system can be implemented progressively, and we have highlighted 4 different phases. To summarize, the first phase can be a partial REM deployment, considering just one loss in a part of the network, and the implementation of the dynamic onboard energy management, DOEM, on a limited number of trains. The second phase is similar to the previous one, but in this case, the implementation of the DOEM could be done for the whole fleet. And the third phase consider a complete REMS implementation. That means the implementation of all the subsystems developing inside the REM system, the functions, and consider the whole fleet equipped with the dynamic onboard energy management. And in this case, the mission could be the energy consumption and the power peaks optimization. And the last phase is the most complete level of REMS implementation. It's similar to the previous one, but in this case also can be added the cost optimization missions. These are the contents of this task, and we have explained the different documents we have developed inside Work Package 7. And that's all. Thank you very much.
time for question and answers. So don't go too far, speakers. Remain around here. You can sit down, but I mean, remain focused. So microphones will be circulated as during the first attempt. Any reaction? Any question? I mean, any comment?
My name is Ulrich Meuser, Deutsche Bahn. I have two questions. One regarding to Scenario 1. What was the impact to the schedule? Does the travel time was it longer or not? This was what I was missing. Answer. And regarding to the last presentation, a question: do you have also considered to link the REMS tool to a driver advisory system, so that you immediately can steer or stay in contact with the driver?
I can answer the first question concerning the shift of the timetable, but we can do this together with Olivier. So we just shifted the timetable with no change for the duration of the journey. It was shifted a few minutes before and a few minutes after. And as far as I remember, it corresponds to a gain of about 7 or 8% on the peaks. Is it?
Yes, this is a good order of magnitude. So we have to be careful of this kind of timetable shifting, because sometimes it can lead to energy benefits or power reductions. But if we synchronize the accelerations, for example, it can lead to over peaks. So it's very difficult to adjust, and we have to be careful of that.
But what is important for us, railways, it's proved that there's of course, with the restriction that Olivier said, it's very complicated. But it's proved that there's a lot of, quite a lot of gain to find in this field. That is a little adjustment of operation that could lead to significant gain on the power peaks.
Okay, yes, answering your second question about the driving advisory system. In fact, the DOM is we call Dynamic Onboard Energy Manager, which tackles two parts. First, the driving profiles, and second, the management of the auxiliary systems. Concerning the driving profile, it can be, the system can provide to the driver some hints. This can be shown in the HMI, for example. I'm sorry, this is not it's not a clear image, but here it was implemented in Malaga, the driver advisory system, showing to the driver the speed profiles. The speed profiles are calculated dynamically according to the constraints received from ground. That means if there are, for example, a faulty substation or at a certain point we have to reduce the power demand, the system takes into account these constraints and recalculate the optimum driving profile, adjusting the consumption to the constraints, trying, of course, always to reach the stations on time. But also this system reacts dynamically to other conditions. For example, it can compute also the real weight of the train, depending on the number of passengers. It can compute the adhesion factor. it can compute if there is a degrade mode on the train because there is a failure on the traction or on the brake system or whatever. Okay, and also coupled with delays and so on. But yes, and in addition, we have also not implemented, but we have agreed or designed an interface to the ETCS through the ATO, because there are a lot of similar features. So we had this also taken into consideration, and we were in contact with some groups working on this standard and at UNISIC.
Any other comments or questions? Yes, sir. Could you please shortly introduce yourself to the audience?
Okay. My name is Nozuma Shida from Japan Railways Group. I also have two questions about Scenario 1 in French case. One question is, do you have any other example in the project aside from Macon station? Because 10% of energy reduction of energy consumption is a big impact from Paris to Lyon. So I think there are other example aside from Macon station. And the second question is about advisory system on board. Do you use similar system like ADIF and Renfe scenario? So, or do you any other system to send advice to train drivers?
I will answer the second question and leave the microphone to the first, to Olivier, but I'm not sure I clearly understood the second one.
For me again, I guess.
Okay. But today in the train, we don't have advisory system for the driver to save energy. The drivers, they don't receive orders concerning the speed that will be perfect concerning the energy. We don't have it now.
Olivier, you wanted to add something?
Yes, for the first question. For the first question, if I will understand, you speak about the delays involved by the costing. So, in fact, this is as the train is already late, because the train has to stop at the Macon station. So at the end, the train will arrive at the same time in Paris. So that's just a way to reduce the consumption of energy. We know that the train will be late. So since it's late, let's try to minimize the energy. So it's 10% of energy reduction compared to the conflict situation. But at the end, the train is late. So it's not 10% reduction compared to the train if the train could be on time. So that's. I'm not sure if I answer your question, but okay.
Javier?
Yeah, okay. Concerning the driving advisory systems, well, maybe my colleagues from Renfe may confirm it, but as far as I know, there are only pilot cases in Spain concerning driving advisory systems, mainly static. That means that they have probably pre-calculated driving profiles. We also have some examples in the north of Spain in an operator called Euskotren, a regional operator, that they have static, not connected driving advisory systems, within MERLIN, we have implemented 2 steps further. I mean, the driver and advisory system through the DOM is connected to ground to get energy-related constraints. So it participates in a negotiation of the energy and power trading within all the actors. And the other connection is with the traffic control center. The example my colleague Ruth saw before is when there is some traffic congestion or something like that, that the train receives dynamically a new timetable. So it can calculate in real time a new driving profile adapted to the new timetable. Of course, it must be pointed out that the algorithms are not part of MERLIN. This is, there are competitive issues, competitive developments so they are kept in the expertise of each company, and we are not providing these algorithms. What the project is delivering is a set of proposals for standardization, for interface standardization. So we have developed some interfaces, including detailed description of the data to be exchanged between train and ground, so that it will facilitate later on the implementation and solve compatibility and interoperability issues.
Hello, my name is Mark Turner from Sceanario and Sistemas in Barcelona. I've got one question. It's not specifically directed at anybody. My question is, before I started at Sceanario, I was 30 years as a rolling stock designer. So my question is, when are we going to see specifications that permit the removal of the brake resistors from the trains? Because I mean, when we did some studies, we always say that the trains can regenerate. But when you actually do the studies, it was quite a surprise as to how much work the brake resistors were doing on the trains. They were burning up the energy, and I know it's a big problem in some metros, especially in Spain. The tunnels get very hot, generally from the heat produced by the trains and also from the brake resistors. So maybe there's some operators or even rolling stock suppliers who could comment on when we can start removing brake resistors from rolling stock.
Who wants to answer? Roberto, okay. Yeah.
I don't know if I'm going to give you the right answer, but I'll give you an answer anyway. You're pretty right. Brake resistors is an issue in terms of tunnels for metros and things like that. Creates an awful lot of overheating. And in fact, energy optimization, in particular in urban systems, is all down to temperature control. So it's thermal, basically. So there is already, and my colleagues were from the systems integrators will probably confirm that, but rolling stock manufacturers are looking into using energy storage systems to capture that. So that energy, instead of being burned in the resistors, is captured on the batteries, double layer capacitors, and so on and so forth. So the idea is perhaps not getting rid of them altogether, but try to minimize the effects in terms of temperature increase and losses, because you're basically burning energy. So I don't know if that's the right answer, but I think looking ahead, we are going towards a next generation of rolling stock that would use hybrid solutions for that. I don't know if that answers your question, but... I can give you an answer. There you go.
Some advertising for Alstom. So, well, it pays my plane ticket. So currently, actually, we are doing a lot of bids without in metro without a resistor on board. I can give you the multiple names of this kind of bids, but we are actually not using as a rule a resistor, especially on metro bids and projects. And what we are implementing now, it's the reversible substation. We have a reversible substation which is named ESOP, which I think is quite well known in the railway industry, especially in urban transportation. There is one installed in London at Victoria Station, of course, because of this problem of overheating of the tunnel. Tunnels in London are very narrow. It's the oldest metro in the world, and the boring it was very narrow. And now, as a standard, we propose this reversible substation instead of diode rectifiers. What is interesting is the solution is you can see that you don't need to make a full line only with reversible substation. Simulations and studies shows that you can optimize and you can make a mix of diode and reversible substation to optimize your investment. And this, even if you don't put everywhere reversible substations, you can evacuate a lot of braking energy. And this braking energy is not wasted. It's when you have a medium voltage network, it is injected in this medium voltage network, and it is used by other substation which can draw the energy from the medium AC voltage network. So now it's becoming more and more a standard to propose a system solution. Of course, it's a system solution without rolling stock braking resistor. And I think it will be more and more the same in the future. Okay.
Thank you, Marius. Any other question? Because we nearing lunch break time. One final comment or question? Thank you.
Good morning. It's Vicente González from Red Eléctrica de España, the Spanish TSO. I have 3 questions. One is quite general for any of the speakers, and the other 2 are also related with scenario 1. One for Eric and the other one for Olivier. The first one is, as you probably know, in the power sector, we are talking about smart grids for more than 10 years at present. And we used to decorate all our slides or proposal with a lot of very black figures showing a lot of profits for all the actors involved in the business. And I'm a bit surprised because I didn't see any economical assessment behind all the different proposals discussed this morning. I missed the first session, perhaps. I was wondering if there are some cost-benefit analyses supporting the different proposals, or what is the stage of this evaluation. The second question to Eric, it's very easy. I was wondering if you have discussed the different solution with my mates in RTE, and what has been their feedback about the different solution proposed. And the third one to Olivier, it's related to the third solution proposed, that in my understanding, perhaps I'm wrong, it's basically a new substation but not connected to the grid. Which is the advantage of this solution in front of a new substation directly connected to the grid? It's only a question of investment cost, there are something else that I cannot see this morning.
So, okay. Speakers have to decide among themselves.
So there's several questions. First, the easy one concerning if we coordinate and talk with RTE about this subject, about this solution. No, we didn't talk with RTE because anyway, we know that where we have the problems in the Morvans Hill, RTE is very weak, and to bring power for a new substation, it would cost a lot of money. So this is an important point of this problem. Is that the fact that RTE is weak in the Morvans Hill, and that's why there is such a long distance between the two substations, Surrey and Commune. It's I don't remember exactly, but it's almost 100 kilometers, and that's why we have this specific problem. So this was the easy answer. There's another question, which was the first one, if I remember well, concerning the financial aspects. Yes, there's no cost presented in this in the slide, and to be honest, we didn't dig so far the financial aspects because what we want to do is to improve the line capacity, and it's this line capacity which will bring the money to the system. It's not. We are convinced that it will not be only the economy of energy that will allow to pay the new system. It's not how to say that. Today, electricity is not expensive enough to bring to permit to make such a big investment, and and to improve the capacity, there are several issues. There's electrical issue, but there's also another kind of issue which are related to blocks and things like that, or other railway issues. So we didn't. We have no figures we didn't dig so much into the economical field, but there's something positive, anyway on this economic field, is that the technology concerning storage of energy is evaluating now quite fast, and the prices are going down, and so we have good hope that to make a storage substation, an energy storage substation, it will be cheaper than in the next year than it is today.
Okay. Very, very briefly, because now we're getting late.
Okay. Well,
we were in advance, but we're getting a bit late. Thank you.
No, just a couple of things, because I think the question from your side is the question regarding the cost-benefit analysis is very pertinent. Well, actually, I would like to say first that we've done economical analysis, but the estimation of the cost is something that we haven't been that able to perform. So we have an idea of which would be the savings and would be the impact of these savings in economic terms. We are probably in a more preliminary stage than you are in electrical transmission and distribution. I would like to highlight one thing. The problem is slightly different. When we talk about smart grids in Just, the electrical sector. We're talking about capacity utilization and how by using a smart operation of the grid, I can save in wires, in new lines, in new substations, etc. The goals of these smart grids are quite related to that and to quality ensurement in the distribution part. A railway smart grid is a little bit different because we have to combine two things. First, to provide a railway service. The primary purpose of a railway smart grid is not to deliver electricity, it is to move goods and to move people on time and with given constraints of punctuality or time of trips, etc. And for us, the power part is like a secondary objective, which is always supedited to the first one. The grids in railways evolve much faster than they do. We have really strong variation from 100% to 20% and then back to 100%. And this makes that from a computational and TI perspective, it cannot be managed exactly as it is in others. So we're taking the experience of other sectors, but we're trying to adapt that. And for that reason, we are still in a more preliminary. I think the economical analysis, the conclusions will be available in the public documentation, so we can discuss it in a more informal situation. Thanks.
Thank you, Eduardo. Thank you, everyone. So if you have more questions, we'll have a cocktail reception in the afternoon. So I think that's the perfect occasion for you to discuss more into details, very technical topics that you would like to know about. Okay, so now let's have lunch. Now I would also, sorry, it's upstairs, okay. Maybe I will ask my colleagues from FFE to show the way. But before that, can you please make noise for the speakers, because they did a good job. Thanks very much. Enjoy your lunch. Thank you.